Hello everyone, I'm Alex, and today I'm going to tell you about a project I've been working on recently. It's basically a type checker for Python, written in Python. It used to be called Pyro, but not anymore, because as someone in the Python community pointed out, Pyro is already taken. So now it's Python Dash. Okay, sorry about that. Okay, it's called Python Dash. I'm not going to tell you why right now, but it's going to be obvious by the end of the presentation. So first of all, I'm a software engineer at least, and I'm also a language geek. So that gives you plenty of reasons to ask me questions. I'm going to do some geeking later on. So what's List? List is basically a fashion aggregator. It's kind of an Amazon of fashion. And List loves Python. Basically because the founder loved Python. Now, 5 years later, we have 350K lines of it. And we have around 30 engineers making sure that those lines don't break. And it's not as easy as it sounds. Because Python is nice and cute when you start prototyping your system, and you can get out the prototype in 1 weekend. But 5 years later, it's not going to be all fun and games. Because basically when you just refactor something, you have to be sure that you didn't touch the bad method or that you didn't change all the parameters. So it's not that much fun. Basically, we do around 5 to 10 deploys a day. And basically, we optimize for a fast deploy time, not because we want to be like super agile, but because we have to fix stuff, right? So when you deploy something, it's not a matter of not breaking it. It's a matter of finding out as fast as you can that you broke it and fixing it. So that's why we optimize for fast deploys. And I personally have a strategy which is called deploy and pray. So one important detail is that our deploy process involves a deploy token, which is Rainbow Dash, right? So whoever wants to do a deploy has to get a hold of a plushie of Rainbow Dash, and then you can do the deploy. This is a very important detail. So we also have some static checks in place. Well, if you can call pylint and flake8 static checkers, because they're very superficial. And also a lot of monitoring. So basically when stuff goes wrong, and it will go wrong, you get a lot of emails. You know that you broke something. So that helps us keep the site running. And our errors look something like this. And if you look at them, you'll see that they are all Python type related. That's because Python has a latent type system, which means that it only detects stuff at runtime, which is fun because by runtime, your stuff is on the server. People can reach it. They can break it. And I find the last error, the one with takes 5 arguments, 5 given, really interesting. So you have to deal with stuff like that all the time. Okay, I already mentioned my policy. I'm not sure if it's smart to repeat it. So when I came to this company, I was just finishing my PhD, and I said, okay, this sucks. Let's rewrite it. But it seems that it doesn't work like that in the real world. You can't just go around rewriting 350,000 lines of code. I don't know why, but they didn't let me. So being a language geek, I said, okay, I'll write a type checker. How hard can it be? Famous last words. So I had to set up some goals for my type checker. Given that we are using Python 2, we can't use any type annotations because Python 2 just doesn't have them. So it means I'm going to have to do global type inference, which is hard. It should also allow idiomatic code because our Python developers want to write their code in a certain way. So it should allow those code patterns. And also it should have good error messages. Not like, these types don't match. Go figure out where it's gone wrong. So it should point out the error fairly nicely. Before I go any further, yes, I've heard of MyPy. MyPy is another Python static type checker. And Guido, the guy who invented Python, decided to integrate it in Python 3.5. But once again, we're using Python 2, so no J for us. And also, Python is mostly a has mostly a structural type system. So how many of you come from an academic background? Okay. Are you familiar with structural typing versus... Sorry for that. Are you familiar with structural typing versus nominal typing? Do I have to explain what that is? Cool. Okay, cool. So it mostly boils down to a simple question. I have two types. I have foo and bar. They both have a method called m, and then I instantiate them. The question is, do O1 and O2 have the same type? Now, if we had any academics in the audience, it's a very hand-wavy definition of same. Okay? So, do they have the same type? Well, a nominal type system would say no, because they have different names, right? One is foo, the other is bar. They don't match. That's what C#, Java, C++, and other mainstream languages use. A structural type system would say, well, they look kind of the same, so, okay, they have the same type. Now, this is really interesting when you're dealing with methods, right? Let's say I have those two objects, and I also have a function, which receives some object O. It doesn't know what its type is, but it wants to call a method m on that type. What should the type of f be? Well, Python says, if it has a method m, I don't care, I'm gonna use it. That's basically called duck typing, because if it walks like a duck and it quacks like a duck, it must be Python. So, Pyro is a bidirectional constraint-based type reconstruction algorithm with row polymorphism and union types. It all sounds really fancy, and that's it. So, coming back to our example. We have our two classes. We have our method. Let's see what Pyro decides the type of f should be. So I already have this example open in Vim, and if I run Pyro, can you all see the writing? Should I make the font bigger? Is this better? Okay. Okay, so Pyro says, well, f has that ugly type, right? Which isn't actually that hard to read. It basically says, if you give me any object which has a method m that doesn't receive any parameters and returns any type, I don't know what the type is, I don't care, it's some type, I want to call it t6 because I hate you, I will give you back that t6. Right? Because I'm calling the method and I'm giving you back its result. So this is what Pyro thinks the type of that method should be. But how does it get to that type? Well, first of all, it looks at foo. And it sees that foo has a method f, it doesn't receive any arguments, and it doesn't return anything, right? So the type of foo is just a record with a method m with that signature. It looks at the type of bar, which has the same type, as I said before. And then it decides that f should have this type. Why? Because I'm calling m on my object O. It doesn't really care what it is. It should only have a method m. Okay, but things get interesting. What happens? Yeah, probably. Okay, I will just stay in this part of the stage. Okay, so what is the type of f now? I'm also returning the object from the function. Well, it's obvious. I receive that, I will give you back that, right? It's quite simple. But this kind of breaks down, because if I also add some methods, another method n to each object, so sorry, in bar, the second m should be an n. It's my fault. So if I add another method, f doesn't know about it, right? F only knows that its object should have an m. It doesn't know that it should have anything else. So if I happen to call f with one of the instances of foo or bar, then I'm losing information, right? It doesn't know about it, it doesn't care about it, it just throws it away. That's what row polymorphism tries to solve. It has a weird name, it's kind of academic, but it's actually a really simple concept. It says, well, if you have these objects and you are trying to use them, you only tell me about m, but I'm going to assume that your objects also have some other properties. I don't know what they are, but I will just put them in a variable. And that variable is called row in the literature. So don't blame me, that's what the guys used. And as you can see, the very important bit is that it's also returning row in the result. So basically, it's remembering anything that it doesn't use. It doesn't use it, but it remembers it. That's the key point of row polymorphism. So in this case, row would just be another object which has a method n, and my object has two methods. Now it all works out nicely. So, yeah.
When you run Pyro, you run it ahead of time or also at a runtime, because types change. And also, if you have two methods that are the same and take just self, you could then rewrite one of them to have one default argument. I don't know that can be called, but can
that's a very good question.
Do a lot of wild things with that. So you cannot do really at ahead of time this kind of things.
Of course, you have constraints because Python is a really, really magic language, and it allows you to do crazy stuff, which just don't fit in a static type system. Of course, I've had to cut out stuff. But as you'll see later in some examples, it maintains some nice bits of Python. So I'm just trying to make it harder for people to shoot themselves in the foot. Right? Yeah, sure.
So earlier you said that you couldn't use type annotations because you're in Python 2.7, but if you look at, for example, the Google Closure compiler, they've done a lot with type annotations despite JavaScript not having a syntax for that. So did you consider that kind of solution?
Yes. So there are a couple of alternatives. One of them is just specifying annotations in comments, which doesn't work because I'm using the Python AST module to parse the source code, which doesn't keep comments. It throws them away, so that's no go. I can also use doc strings. So for those of you who are not familiar with Python, Python allows you to put a string at the beginning of your function or your class, which is just documentation. Basically, I could parse the doc strings and extract type annotations. Our code base does have them in a couple of places, so we just say this parameter has type int. And I could use that. I haven't implemented it, but I can implement it, and I probably will, because global type inference is hard. Any other questions? Yeah. Sure. Where? Tell me when to stop.
Yeah, there.
Here. Okay.
Yes. So here you say that f has returns a unit.
That's actually nothing. Unit void.
Yeah, yes. And that m also does that, but f doesn't need that, right? Like f could also work with an object that where m returns something.
Yes, that's a simplification. That's actually a type variable there.
Oh, okay.
So that's, you're right in pointing that out. Anyone else?
Related to this question also, the two methods can return void or unit in some cases, and a value in others. This is allowed by Python. So you can.
I'm not sure. I'm not sure I understood your question. Can you?
It can change the return types also from the methods. So you cannot be sure of what is returning from one method.
Are you referring to cases where I might return some value on the then branch of an if? Yeah. I will talk about that a bit later.
Okay. Sorry.
No worries. Okay. So how exactly does Pyro decide which type f has? Well, it traverses the abstract tree of the program. So basically, you can represent any program as a tree, right? And then it just visits that program, and it assigns some made-up types to expressions. It doesn't know what the types are, so it just uses some placeholders, which are called type variables, because they are variables which hold types. So it looks at f. F is a function. It receives one parameter, and it returns something. I don't know what. So I'm just going to say it gets an alpha, and it gives you back a beta. I don't know what they are. I don't care. Now, since O is the first and only parameter of f, it's going to have type alpha, because that's the type of the function. And now it looks at the method call, which is another type, gamma. I don't know what it is. Okay, so this is the first part of the algorithm. I'm just assigning type variables to expressions. Now it's time to collect constraints. Basically, a constraint is an equality. Every time I call something, a method on an object, or I do something which should tell me that two types are the same, I add one of these constraints. So in this case, because I'm calling the method m on the object O, I say, well, I think that alpha, which is the type of O, should be an object which has a method m, which receives some parameter, delta, I don't know what it is, and it gives me back a gamma, because that's what I'm returning from my function, right? And it might have any number of fields, I don't care about them. And then it says, okay, I'm calling m with no arguments, with unit, so gamma should be unit. And finally, delta should be unit. And finally, gamma, since gamma is the result of m, and that's what I'm returning from my function, gamma should be the same thing as beta. And it ends up with this. This is basically what I showed you earlier in the console, just with a nicer notation, right? So f is a function that receives any object which has a method m and any other fields. That method returns something which I'll give you back. To be fair, the full type is this, because I can abstract over that beta, it can be anything. And also, because I already have a field called m in my object, I don't want it to appear in my other fields. I don't want to have two fields with the same name. So there are restrictions on the type variables. In this case, it tells me that, okay, your type variable can hold an object, but that object can't have a field called m. So that's basically it. That's what Pyro does. And a lot of magic. So the example I showed you earlier is not really the simplest example you could use, because I could have used something like add 1 to a variable. But in Python, that's actually a method call, because Python has a data model which says that some magic methods, and magic methods in Python are those ugly things with underscores in front of them and after them. It tells me that some magic methods can implement operators and common operations, right? In this case, I only show 3 of them, which implement the plus operator, the minus operator, and the multiplication operator. And now let's see an example which uses a plus operator. So in this case, I have a very, very small font. So in this case, I have a function which just increments a value. It receives an n, and it returns n plus 1. Then I just call my function with an integer. So what should the type of inc be? Let's see what Pyro thinks. So in this case, it tells me your type is that thing. Good luck reading it. So it's telling me that it's something that should have an add method, which receives an int and gives me back an int. And the other methods are there just because ints have them. It has an comparison operator, subtraction operator, equality operator, and so on. And it gives me back an int. And the type of my variable here, the result of calling inc with an integer, is correctly identified as an integer. Right? So that works out. Now, what would happen if I would uncomment this line and try to type check it again? Well, it should fail. Hopefully, it will fail. And it failed. And it's telling me, okay, the first argument of the function you're calling is a string. But the function wants something that can add an integer to it. You can't add integers to strings because it doesn't make sense, right? So this rejects the type error in a very verbose way. Okay, so those are magic methods in Python. So how exactly No, it was Command P. Go away. Okay, so how exactly do I decide if types match? Because that's the most important thing in the type inference algorithm. Well, I use something called inserters, which is an algorithm developed by Mark P. Jones and a co-author back in '94. So by academic standards, it's like ancient. But it works out really nicely with type inference. It has some drawbacks, but I'm going to talk about them a bit later. So basically, the question is, if I have this record, which has a label L, a field L, which has type tau, some type, whatever, and it may have some other fields, how can I say if it's the same type or if it's compatible with another record which has a label L prime, which is different from L, and another type? So what the algorithm does is it walks over the first type label by label, and it tries to find it in the second type, right? If it can do that, if it invents a new variable, it assigns the new label and the type to that variable, and it goes on for the rest of the variables. Basically, this has a very bad time complexity, because if you're unifying big types, it can get really slow. And unfortunately, in structural typing, you get big types. So the algorithm is quite slow. That's one of the drawbacks. Now I'm going to show you some more examples, so feel free to interrupt me, ask questions. That's why you're here. Yeah.
I have a few questions. Like before in the example where you add a string with an integer.
Yes.
I don't know much Python, but can you reopen the string class and add method to it to accept an integer?
You can do that, and if you do that, it would work.
So it takes into account that. And how do you deal with code that's written in C, the methods and all of that?
That does not work.
Okay. So you are hard coding all of that for the standard library?
Yes, unfortunately, I will have to give type signatures for the standard library. Or I could try to infer it, but that's probably not going to work.
No, I think that the same solution is like...
Yeah, unfortunately, you have to do that in latently typed languages.
Okay, thank you.
Thank you. Okay, I think there's a question here in the front row.
When you had the line where you assign the y, when that was commented out.
Because it doesn't make any sense.
Yes. No. When in this state, the type that you infer for ink.
Yes.
Assumes that the argument is an integer.
That's a very good point, and that's an unfortunate side effect of how inserters work. They just, when they unify two types, they just propagate methods, unfortunately. I can work around this, but in this version, they will pollute the type of the argument.
But isn't that really problematic when you put this function in a library and you don't know the call sites yet?
No, it doesn't care about the call sites.
Well, but what if I wanted to call ink with a double?
That will not work.
But in
this implementation.
But in simple Python it would, right?
In real Python it would work, yes. That's basically a problem of the fact that it's treating +1, the 1 in +1, as an integer. So it's propagating the type information from the 1 in the signature of plus, and that's why it's getting integers.
Yeah, but
I know basically it means that plus is not polymorphic.
But the plus only assumes that the n needs to have an __ add method, right? It doesn't assume that it's integer.
That's a very good point. It depends on how you define the plus. So in my case, plus is defined as, after very, very much code which lives in only one file. Don't do this. Okay, so plus is defined as this. Add, which is a function type, which gets a self type, and it gives you back the same self type. So the type signature of the plus, of the add operator, is intentionally very narrow.
So you say they both have to have the same
Yes.
type, and then when the second one is the integer.
If I want to make them more generic, I could insert type variables here and generalize them. But that doesn't play very nice with union types, which I'm going to introduce a bit later.
Is it possible to type something that's actually generic on several kind of input types and does something? So, for example, can you type something that takes an integer or a float in your type system?
At the moment, no.
Okay.
So I'm going to go into details in a little bit. Okay.
We have another question.
Oh, cool.
So isn't this lack of polymorphicity a serious issue in the, I don't know, 100,000 line of code base?
So in this implementation, it is a serious issue. It's an issue with numeric types, to be specific. It does
only with numeric types?
Yes, only with numeric types. Because you have to bootstrap your type system somehow, so you need some base type, like integer and so on. Basically, this problem arises because I chose a very narrow signature for the add operator of integers. They basically say, I want an integer, I will give you back an integer, and that information propagates. So it's kind of the same problem you have in languages like OCaml and, okay, OCaml is a good example, where you can't use plus to add integers and floats, and you have to use a different operator. This can be worked around. I just haven't decided what the best solution is, if I want to use a union type or if I want to use a more permissive signature for the add operation. So I'm going to raise this question at the end of the talk. Yeah, cool.
Do you know typed Lua?
No, I'm not familiar with it.
It's an attempt to type Lua,
Okay.
and so maybe it's worth to compare with your approach.
That's interesting. Does it use type signatures or does it do global type inference?
They use optional type annotation.
Okay, those kind of help.
Yeah, I think they use gradual typing.
Yeah, that's a nice approach.
How do this work with object hierarchies? So, for example,
I will show inheritance a bit later. It's in one of the next examples. Other questions? Okay, so I think someone had a question about using generalizing over multiple type variables. In this case, this is a polymorphic function, just to show that polymorphism is there. The type of ID, which is a function which takes anything and gives you back the same thing, is just for any type variable, for any type I may have, for any type you give me, I will give you that type back. And this works for multiple arguments. So if I add another y here, it will just say, I have two types, I'm going to give you back something. So next we have classes and objects. Here we're defining a very simple class called C, which has a method which takes the self parameter and some x. And let's see what the type of C is. It's just C. So because types are so awful in structural type systems, Python dash, okay, it's not Pyro anymore, Python dash tries to give you the name of the type when it has it. So whenever you define a named type, it will remember the name as a tag, and it tries to show you that tag whenever it can, right? And now let's see what type of O should be and what the type of calling the method is. So we are instantiating our class here. The type of O should be C, and then we are calling the method, which should give us back an integer, because it just gives you back what you give it. And in this case, it works. Now, I can also call the method with a string, and it will give me back a string. Nothing very special here. Basically, it should just work. Okay, what about self-types? We haven't talked about them, but they're actually very interesting, because recursive types are not that straightforward to implement, or not always. How do you type a recursive type? Well, there are two approaches. One of them says, I have this record. I introduce a special type variable, which is my self type. And then whenever I call a method on that type, or I access one of its fields, I'm going to replace the self variable with the type itself. Right? So that approach is called iso-recursive types. And it basically says that the type is equivalent with its level 1 unfolding. So that's what Python dash does. And in this case, we have a class C, which has a method, just receives the self argument, and it returns it. So in this case, I should be able to call the method repeatedly because I'm just returning the same object. And the type should always be C. So in this case, if I type check my program, I see that O has type C because it's an instance of my class C, and then again X is also C because it's self, right? I'm going to run this in the verbose mode to show you what's actually going on, and there's a lot of things going on. Basically, these are the steps that Python dash is following to unify stuff. So that's what types actually look like, but because they're kind of hard to read, it tries to give you back nicer types. Okay. What about constructors? Objects, classes can have constructors, right? How does Python dash handle them? In this case, we have a simple class, C. It's a counter. It receives an initial value. It remembers it in an attribute. Then you have an increment method and the get method, which will give you back the number. So it's the same situation as before with the integer because I'm adding 1 in increment. The information propagates, and the type of C here is a constructor, because in Python you can just call the name of the class as a function, and that acts as a constructor. In this case, I have a constructor which receives an int, and it gives me back a C, the problem with non-polymorphic plus. And now if I call the methods, c.inc, oops, it works. It shouldn't print anything. Okay, and finally, since we're talking about objects, we can also have inheritance. Let me scroll up. Here I have a base class which has a method m. I have a derived class which has a method n. The derived class is derived from base, so if I instantiate a derived class, I should be able to call both m and n on it, but I shouldn't be able to call n on the base class. So this should throw a type error. So if we try to type this without calling n on b, it actually works, and they all have the expected types. But if I uncomment this line here, it throws a type error, and it tells me that the object does not have an attribute called n, which is expected. Basically, Python dash treats inheritance just as copying properties from a base record to another record. It's just basically extending records. It does not create a subtyping relation, because the subtyping relation is replaced by row polymorphism in this case. Subtyping doesn't work that nicely with structural typing and type inference. That's why I chose this approach, and I think it works nicely for Python. Okay, and finally, one of the last features I want to introduce is union types. In this case, it means that a value can have multiple types. One of the simplest examples is this function, which receives a number, and if the number is greater than 0, it just returns the number -1. If I type it, I see that this is the important bit down here. The type is, oh, you can see it, right? The type is non-type or int. So because it only returns on one path of the function, by default, Python returns none from functions that don't return anything. So in this case, the return type is either none or int. And if I want to use this, if I try to say y equals x plus 1, I'll get a type error telling me that the type of x is actually a union, none or int. And if I want to use it, I should use a type test, which is instance or is not none check. One of the goals was to give nice error messages. I think that this error message is quite nice. Not all of them are as nice, but it's getting there. So let's make this actually work, and we say if x is an instance of an integer, this is Python's way of asking, are you an integer? This should work, and the type of y is int. Now, this has one drawback. The fact that its instance in Python actually uses a subtyping relation which Python defines. In this case, because Python dash does not define that relation, this is not going to be transitive, right? So if I wanted to test for a derived type, I wanted to test a derived type if it's a base type, that's not going to work, because it's not doing structural unification inside union types. It's just doing simple matching. So that's one of the open issues. So I think that mostly covers the demo part of the presentation. Now, as I said, the types are quite scary if you look at them when they're unfolded. One open question is, do row polymorphism and union types interact well? I think that if you use union types everywhere, it's not going to play nicely with row polymorphism. But you can use union types for a very restricted purpose, like nullable types, the example where I returned either int or none, and other cases that are similar. But I think that generalizing it for the whole language might have some weird interactions with row polymorphism. Now, you might remember seeing this. Yeah.
So, do you do anything to try to type check uses of classes as values, like creating mix-ins or anything like that?
No, at the moment, classes are not first order. They can be quite easily. That's not it's not a shortcoming of the system. It's just that I didn't implement it. Classes are just objects. So
so I recognize that in Python, classes are just objects, but I don't think it's just a small matter of implementation to type check that. There's a lot of tricky aspects of that.
Okay, we can take this offline?
Or I encourage you to come to our eCoop paper later this week.
Cool. So you might remember seeing this flyby on the screen earlier. This is the reason why it's called Python Dash. If any of you guys watch My Little Pony, I don't, but my colleagues do. It seems that Rainbow Dash gets angry a lot, and this is her angry face. And because Python Dash screams at you, and it's quite colorful, that's why it's called Python Dash. Okay, it's alpha code. It's mostly a proof of concept because your SSD crashing does that to your project. It's open source. I'm gonna put it on my GitHub account. And finally, thank you.
If I may still, do you have some way to distinguish between something being a union type and something being a type error? For example, if you assign two types to something, does it get a union type or is it a type error?
That's one of the points where I said that union types and...
Can we keep the volume down so he can answer the question?
So that's one of the problematic points of union types and Python's semantic. Basically, in Python, when you don't really have assignment. Whenever you assign to a variable, you're actually defining a new variable. So it's all a matter if you want to think of assignment as introducing a new variable or just updating a union type with a new type, right? And I personally have a strategy which is called deploy and pray. So one important detail is that our deploy process involves a deploy token, which is Rainbow Dash, right? So whoever wants to do a deploy has to get a hold of a plushie of Rainbow Dash, and then you can do the deploy. This is a very important detail. So we also have some static checks in place. Well, if you can call pylint and flake8 static checkers, because they're very superficial. And also a lot of monitoring. So basically, when stuff goes wrong, and it will go wrong, you get a lot of emails. You know that you broke something. So that helps us keep the site running. And our errors look something like this. And if you look at them, you'll see that they are all Python type related. That's because Python has a latent type system, which means that it only detects stuff at runtime, which is fun because by runtime, your stuff is on the server. People can reach it. They can break it. And I find the last error, the one with takes 5 arguments, 5 given, really interesting. So you have to deal with stuff like that all the time. Okay, I already mentioned my policy. I'm not sure if it's smart to repeat it. So when I came to this company, I was just finishing my PhD, and I said, okay, this sucks. Let's rewrite it. But it seems that it doesn't work like that in the real world. You can't just go around rewriting 350,000 lines of code. I don't know why, but they didn't let me. So being a language geek, I said, okay, I'll write a type checker. How hard can it be? Famous last words. So I had to set up some goals for my type checker. Given that we are using Python 2, we can't use any type annotations because Python 2 just doesn't have them. So it means I'm going to have to do global type inference, which is hard. It should also allow idiomatic code because our Python developers want to write their code in a certain way. So it should allow those code patterns. And also it should have good error messages. Not like, these types don't match. Go figure out where it's gone wrong. So it should at least loves Python. Basically because the founder loved Python. Now, 5 years later, we have 350K lines of it. And we have around 30 engineers making sure that those lines don't break. And it's not as easy as it sounds. Because Python is nice and cute when you start prototyping your system, and you can get out the prototype in 1 weekend. But 5 years later, it's not going to be all fun and games. Because basically, when you just refactor something, you have to be sure that you didn't touch the bad method, or that you didn't change all the parameters. So it's not that much fun. Basically, we do around 5 to 10 deploys a day. And basically, we optimize for a fast deploy time, not because we want to be like super agile, but because we have to fix stuff, right? So when you deploy something, it's not a matter of not breaking it. It's a matter of finding out as fast as you can that you broke it and fixing it. So that's why we optimize for fast deploys, point out the error fairly nicely. Before I go any further, yes, I've heard of MyPy. MyPy is another Python static type checker. And Guido, the guy who invented Python, decided to integrate it in Python 3.5. But once again, we're using Python 2, so no J for us. And also, Python is mostly a structural, has mostly a structural type system. So how many of you come from an academic background? Okay. Are you familiar with structural typing versus, sorry for that. Are you familiar with structural typing versus nominal typing? Do I have to explain what that is? Cool. Okay, cool. So it mostly boils down to a simple question. I have two types. I have foo and bar. They both have a method called m, and then I instantiate them. The question is, do O1 and O2 have the same type? Now, if we had any academics in the audience, hello everyone, I'm Alex, and today I'm going to tell you about a project I've been working on recently. It's basically a type checker for Python, written in Python. It used to be called Pyro, but not anymore, because as someone in the Python community pointed out, Pyro is already taken. So now it's Python Dash. Okay, sorry about that. Okay, it's called Python Dash. I'm not going to tell you why right now, but it's going to be obvious by the end of the presentation. So first of all, I'm a software engineer at List, and I'm also a language geek. So that gives you plenty of reasons to ask me questions. I'm going to do some geeking later on. So what's List? List is basically a fashion aggregator. It's kind of an Amazon of fashion.